Okay, then hello everyone, this is József Nagy here and welcome to my newest live stream here where I'm going to continue previous tutorials where we took a look at a 2D flow, a flow around a circle, and we compared it with another tutorial from YouTube with a FOAM tutorial, and qualitatively it was a good agreement. Now I would like to do the same for 3D and possibly in future live streams compare it to actual CD curves and then see how good OpenFOAM is and how good I am, and with your suggestions hopefully we as a YouTube community are, and we can hopefully do some great simulations together. Okay, so for this I posted on Monday a poll on YouTube what you guys think would be the best turbulence model to calculate the drag around a sphere, and as you can see here the poll is very clear. So you guys think that the K omega SST model is the best suited, at least in the four that I showed you here. So K omega SST, capture Luminar to turbulent. Of course we are going to do this K omega SST, and then LAS. Yeah, so it's, and here is another suggestion is that K epsilon and Smagorinsky are not very good, so SST is a good idea, and possibly another LAS model. So there are a lot of ideas of you guys that we can now utilize in the simulations, but first we have to create the mesh. First the geometry, then the mesh. Okay, so I hope that you can hear me, that the audio is clear. If you have some issues with the audio or it is not loud enough, then just let me know in the comments below the live stream. Okay, so then what I will do now, I will think about the geometry. So as I mentioned, I'm just going to do a sphere here. Okay, so I'm using Blender, but we could use any kind of geometry preparation tool. So I'm just going to add here a UV sphere with, maybe we should increase the resolution, because if we need fine cells around this sphere, then we will see the edge, the STL edges here. So possibly just 64, no, let's go big. Yeah, that's better, that's a smoother sphere, and I think I'm going to use a diameter of 1 meter. If you think that's a bad idea, just quickly let me know in the comment section. So I'm just going to use a radius of 0.5 and use this as a sphere. Okay, then let's just save this as in the documents, YouTube live, and then let's create a tutorial 3 here. And yeah, so let's just create here a geometry folder, just like the way I like it. Sphere.blender file, and then I'm good with that for Snappy Hex Mesh. Let's see whether we create CF mesh or not, but let's start with Snappy Hex Mesh. Okay, so for that I'm just opening up a terminal. I load OpenFOAM version 2012. So I go to my YouTube live tutorial 3. Okay, and now we have to set up the mesh, and I am doing this from scratch. For your guys' benefit, just so you don't have to. So let's just think about the best tutorial. Maybe a meshing tutorial. So version 2012. Maybe I just put this on. Okay, and then meshing tutorial, Snappy Hex Mesh. Oh no. Okay, and then maybe the best is the flange tutorial. Yes, let's just copy the flange tutorial here and then call it mesh. We don't need the all run scripts. What is in constant? Yeah, we have try surface. We don't need the readme file. We need the geometry files. We did not export it yet. Okay, so now I'm just going to export it. ASCII object mode and delete this. Okay, good. Sphere dot. What happened here? Export STL. Okay, so it is in tut3. It's a capital sphere. Okay, no problem. Sphere.stl, and if you don't have a sphere.stl in this format, then make sure to check out one of my YouTube short videos. There is a hack for Blender how to best modify the Blender script behind the STL export to have the best STL formatting for Snappy Hex Mesh. Okay, then I just create the open.foam file. Good. And let's go into system. Here we have a couple of files, so let's just explorer.exe and open up an explorer here, and let's just start with here a block mesh dictionary, and possibly we could even load everything else here. Okay, so mesh quality dict is the standard quality. I'm just going to use this. The FV solution and FV schemes are default settings here. We are running it on one core, so we don't need decompose bar. Control dict is also just a dummy file. So all we need is surface feature extract, block mesh, and Snappy Hex Mesh. So these are the three major steps during meshing with Snappy Hex Mesh. And so we have here the sphere.stl. And now let's think about the best angle here. So I guess 150 should be good. Maybe we check this. So if I execute surface feature extract, okay, and then open a paraview here. Currently we don't have a mesh, so that we don't see anything, but now here I can load in this edge mesh object file, which is white, so I'm just turning it to black. Okay, so that is very interesting. Extended sphere edge. Okay, so there's nothing inside, so maybe it's not such a good idea to use 150. So 85. What if I just use 185? It's still not the best. 180. Now we have something. Okay, so if I just reload it, so 185 was not a good idea. 180 now has all the edges, if I will, yes. So now we extruded all the edges here from the STL file. Okay, so that's perfectly fine. I'm not sure whether we need here the edge files, but for later tutorials this may, so for later shapes, if we are interested in, I don't know, a cube or something else with sharp edges, then we have to take care of this here. Let's just leave it at 180. We could later go to 170, but that's fine. Okay, so now the initial mesh. So my diameter was 1 meter. So possibly we have to come back to this point at a later time when we realize that our geometry or domain is too small. So if I take a look at this here, so maybe I just put here a cube and let's just make a wireframe here. Yeah, so if I just take a look at this cube, so this distance is a bit too small for my gut feeling here, so maybe let's make it twice as big. That is better in my opinion, and additionally I would like to move this from -1 to -2 and this to 2. Okay, so now we have a region of interest. So I'm not sure. Yeah, so this, so if the flow is coming from the left hand side and going to the right hand side, then this flow is okay in my opinion, but possibly we should extend here the domain a bit further downstream. Maybe even 5. Okay, let's go for 5. Okay, and now I'm just saving this, and then let's just use these settings. So in the X direction we go from -2 until +5. Okay, so -2 to 2 and 2 until +5, 5, 5 and 5 and 5. Okay, so in the Y direction we go from wait, did I scale this transformation? Okay, so we are going actually from -4 until +10, so I did not scale it first. Okay, so here it's actually 4 and 4 and 10 and 10. Okay, so from -4 until +10, and then we are going from here -2 until +2 in the Y direction and the Z direction. -2 and +2. And then -2 and +2. Okay. +2, +2 and +2. Okay, and so now how many cells do we want to use here? So the so maybe we just do a first mesh with a very coarse mesh, 14, 4 and 4, which is of course very coarse, so let's just go for 8 and 28. Okay, so that's a first coarse mesh for the block mesh, and now there are these faces. So in this flange tutorial the boundary was in all boundary because the outside was cut away, but now we want to cut away the inside of the sphere, so we have to have more than just one outside boundary for Snappy Hex Mesh because we need an inlet phase and an outlet phase. So if I sharply think about the geometry, so we are going from, that's the minus z faces, so it's 0, 3, 4 and 7. So this is most probably the inlet face. What did I say? This one. So I'm just going to delete this from all boundary, and then we will see afterwards in ParaView whether I'm correct or not. And then we can mix and match. Outlet, and yes, so let's just call this sides, and then what is the outlet? This is the positive, and so that's 1, 2, 5 and 6. Is there some? Yeah, this is it. Okay, let's get rid of this, and now we should have the sides, inlet and outlet correctly, but let's see. This is always very interesting, just to visualize the block mesh in front of you. Good, and then let's go to ParaView. And then refresh the mesh. Okay, so here now we have the mesh with the sphere in it. Yeah, it's very coarse, so we have to refine that, but for first idea, yeah, this is the inlet, and did I get the outlet correct? Yes, very good. So this is the inlet and the outlet. And now is the question, what would be the best resolution? So I'm not very happy with this. So let me just quickly, that's 0.0, so edge length size of 0.05. No, 0.5, so that this is very, very coarse. So we should really increase with a factor of 4 at least, I would say. So what's that? 32, of course, 32 and 112. Let's see this block mesh. Yeah, 114, that's fine. That's a better resolution. Good, and now we can go to the next step, where we go to Snappy Hex Mesh. So we see whether we can add layers here. First, we are not going to add layers. We are going to load the sphere, and I'm just going to recall it to lowercase sphere because I'm 100% going to forget. As you can see, we could have also used this searchable surfaces where we define the sphere here. Of course this works, but if you want to later on take a look at more complex shapes, then we have to use the STL file. So I just want to establish the workflow right now, so maybe later on it is just a copy-paste thing. Okay, so no more than 2 million cells. Yeah, we'll see. I'd like to use at least 3 cells in the layers. eMesh. Let's see, level 1 here, and then sphere is level 1 and 1, and then the last thing is, we don't need this here, and then the inside point. So there is a very, very cool and easy way to do it in ParaView if you have not seen my short video on that. So just load this, and I cannot, so for that we need the sphere. Now we can select the probe location. Okay, so this is very dark. Okay, so now we have the probe location. It's inside. So it's inside. Okay, so where is the probe location? It's here, so we have to move it out of the sphere. It's still inside of the sphere. Okay, usually it's easier. Yeah, so that's not definitely outside. So if I just type here -1, 0 and 0, then that's outside of the box, and now we can just take -1, 0 and 0. Here it was very simple, but maybe it's easier for more complex geometry. Okay, so I see two comments here. So hi Pramod, what is the name of tutorial? This is just a fresh tutorial. There is no tutorial. I copied the original mesh from the flange tutorial in tutorials, mesh, snappy hex mesh and flange. But this tutorial is completely new, so there is no name. We can call it the sphere drag tutorial if you like. Okay, so hi Sarang. Hello József, your videos helped me getting into CFDs. Thank you very much. You're very welcome. I'm happy to help. Okay, so this is now everything, and let's just run here snappy hex mesh -overwrite enter, and then let's wait. Okay, what happened here? Try surface flange mesh is not found. Okay, yeah, that was I was talking too much. Of course, that is called sphere.emesh. Okay. Usually I don't talk while I'm meshing, but oh well. Okay, so now we have a first mesh. So, and I guess the final mesh will be finished once we have the first simulation results, because that's the drawback of turbulent flows, that you never know the y plus value from the beginning, especially if you want to, like I want to try out different Reynolds numbers, so maybe we'll need different meshes for different Reynolds numbers, but we'll see. Okay, so then I want to come here, and now, there you go. So there is the sphere. I'm not very satisfied with the sphere. Okay, so let me just cut through this domain and get rid of the black background. Y normal mesh. Okay, so yeah, I mean, for a laminar case this should be fine. So what I want to check is actually adding 2 layers here. So let me just add here sphere, and I want to add 2 layers, an expansion ratio of 0.5, final layer thickness. We'll see whether these settings are okay, but I just want to see how well Snappy Hex Mesh behaves. Let's just delete this round block mesh and Snappy Hex Mesh. That's not the correct way. Overwrite. Okay. Hi Nidal, why not run the mesh in parallel next? Because I'm fine waiting for a minute. Later on, of course, we can run it in parallel. I do have a couple of cores on my laptop. So hi, Lovelyette, I hope I pronounced it correctly, otherwise I'm really sorry. Do you not worry about Kuro number during meshing stage? I always worry about the Kuro number, but after 12 years of CFD or even more, you just are hardened and you just see that's quite Kuro number is very similar to the Y plus value, so usually you only know after once you start the simulation where you end up. So yeah, we can think about Kuro number, but currently I do want to start with the Luminar case. So there I don't worry about the Kuro number, we can use a coarser mesh. But with time, so this is why I want to establish a workflow, possibly set up an all-run script, which then creates automatically the mesh and then copies it to the case and then starts the case, because possibly we will need different mesh resolutions for the different Reynolds numbers. So we'll see. I'm not sure. We'll see. Okay, so as far as I can tell here, we did get a 100% coverage with 2 layers, so that's not bad. Yeah, that is good. That is very rare that you get a full layer coverage in OpenFOAM. Yeah, so that's perfectly fine for me for first Luminar case and possibly even first Turbulent case. So, okay, there is another comment. Hi Brendan, I thought for good stability in meshing the cells should be the area max of the neighbor cell. The case, what should be 1.2 times the area max of the neighbor cells? Which cells do you mean? Could you elaborate? Maybe we can then change this. Okay, so this is a fine mesh. Maybe we could push away these transition cells further away, just so we don't have here the transition. What would be the best idea here? Possibly to change this to 10. And then we wait. So yeah, and what I thought about whether it would be a good idea to do this steady state, but I don't think so. So especially for turbulent phenomena, I do think we should concentrate on transient flows and then get a mean value of the CD value and compare that. So yeah, well, I will start with pimple foam and then go from there. Hi Halim, I learned so much from you. Thank you, you're welcome. Okay, we have the 100% coverage, that is great. Okay, yeah, so we could play around with this, but maybe it would be a good idea to just set up a first Luminar case and then take a look at it. And then possibly start something and we'll see how far we come, and then maybe in the next tutorial we second guess the mesh and also the case setup. So I just create a case and copy something from the tutorials here. Tutorials, incompressible and pimple foam, Luminar, not even Luminar. Let's go for RIS and my go-to case here, and then Pitts Daily, and for now make a copy of that, backup 0, and delete epsilon k and the news, and then go for the velocity here. Okay, so then I am just going to start with a very simple case setup here. What am I doing here? No. Open, please. Thank you. Okay, so we do have here the boundaries inlet, outlet, sides, and sphere. Okay, so for that, the sphere is a wall. Inlet and outlet are fine. We are going in the positive x direction, so we really should think about a velocity value here. Outlet, I am more confident with this BC at the outlet, pressure inlet outlet velocity. Sphere is the surface, and then the sides. That's a very good sides. Did I call it sides or yeah, sides? This is a very good question, whether we want to use here slip or not. I may try here slip, but maybe we have to come back to this and rethink this slip boundary condition on the sides. Okay, so inlet is 0 gradient, that is fine. Fixed flux pressure could be an even better one. Outlet is this, and sphere, and then we have here the sides and slip is what I wanted, but I'm not very confident in that. Okay, so there are a couple of points. Okay, so Brandon, sorry, I meant that if the area of one cell is say 1 square millimeters, the area of the neighboring cell should have an area of 5. So do you mean the cells in the layer or outside? Which cells do you mean? Hi Thivin, could you please give some reference on the type of iterative solver which is mostly used in OpenFOAM? Iterative solver. I'm not sure what you mean with iterative solver. The most commonly used solver is PimpleFOAM and SimpleFOAM. Hi Prince, hey József, I have to do a grid independent study from bachelor's thesis. Can you give me some tips? Have a video for this. I mean, this has nothing to do with this tutorial, so a quick idea is to change the grid dependence increase the resolution by a factor of 2, 3 and 4 at least, if not 2, 4 and 8. That's always a good idea. So Nidal, I have a question on Snappy. Is the outcome of your case here a staggered grid? No, meaning the scalars are stored in cell centers, yes. If so, is there a right, wrong way to post-process this? Yeah, let's come to this. Nidal, please come back to this question next time when we are doing the evaluation. Brandon, I found what I meant. In OpenFOAM, I heard as much by cell volume growth rate. Yes, so you in the boundary layer, there are some very long aspect cells next to some very low aspect ratio cells. In lectures, we were told to avoid this. Okay, so you mean this here. So this height is not corresponding to this one. We can easily change this. Going to here, so this final layer thickness is 0.3 here, so we can increase this and we can add more than 2 layers. So this is then a fine-tuning after a first couple of simulations. So we'll see whether these settings are correct or not, but I'm fine with this for now. Okay, so we have the boundary conditions. Let's go for constant. Turbulence properties is laminar for now. Okay, and transport properties is air. That is perfectly fine. Let's see. Okay, so we don't need the block mesh of the Pitts daily case here. Okay, before I come here, so we only need this. For the laminar case, that's fine. GMG, we'll see. Okay, we'll all see about this. So then we have to come back to the inlet velocity. Okay, so if we have a Reynolds number here with our velocity times our diameter, which is 1 meter, divided by our nu, which is 10 to the power of minus 5. Okay, so if I used here a value of this is 10 to the power of 5, so a velocity of 1 would be a very high Reynolds number in this case. Okay, so we have to go to very small velocities. Yeah, so 10 to the power of minus 4 would give us a Reynolds number of 10. 3 would give us a Reynolds number of 100. So, okay, that's fine. Good, so this will run then for a long time. So we'll see. I am not sure, but a first case is now set up. In constant, we still need the mesh. And then let's run PimpleFoam. Do we get an error message here? No. We could have increased the time step size. Let's just do this. We don't need this kind of small time steps. 0.01. Let's see. Yeah, so this is a very slow case, so we'll have to run it for a longer time. Okay, so we just finished. Let me just open here case and then see about the velocity here. Surface. Okay, so not a lot of change here because it's incompressible, so okay. Let's see. Don't want to scale them. What's a lot of arrows? It's not enough arrows. Okay, they are too long, too short. Okay, so now, okay, that's okay. So the first simulation seemed to run. It was a very fast simulation. Good. Oh no, that's not what I wanted. Okay. So now we have a first, yeah, so possibly we'll have to think about here the mesh resolution. Possibly we, as Brandon mentioned, we'll have to think about the mesh here. But for now, at least we have a workflow. Now, maybe there are a couple of questions. So I answer the questions. We set up an all-run script which then does all the commands together and then runs the case. And then next time, until next time, please download the case, second guess the mesh settings, the simulation settings, and so on. And then please comment below the video. This live stream is going to be transferred into a normal video, and then please below that video add your comments what you would like to improve in the case, or you tested and it's better, and what would you suggest for turbulent cases, and so on and so on. Okay, so questions. Prince, Nidal, Brandon, I found. Okay, so Brandon, so you in the boundary layer there are some very long aspects. Yes, okay, so it's just Brandon's last comment, so yes. But possibly we can take a look at it and the influence of the layer onto the flow, especially I guess for the turbulent cases. Okay, so now I want to set up an all run script, and now I regret that I deleted the all run script of the Pits Daily tutorial, because now, oh no, I deleted it from the flange case. That's fine. Okay, now I don't regret it. Okay, so where should I get rotating fan? This is my tutorial, so I am fine with that. Okay, so then let's go and take a look at all run. Okay, so we run the all run script that will go into mesh, and then we go into case, and for now we will just run the application, run application and get application. Okay, so this will then run the simulation for us, and okay, and then leave it at the end. Good, and then the all run the pre-processing step will go into mesh, copy the geometry for STL to constant tri-surface, and then execute exactly these. We could run renumber mesh, that's also a good idea. We don't need these, and then we copy constant polymesh to case constant. Okay, so this is the all run script, and now we really should have an all clean script. All run, all clean. Maybe let's just copy flange, all clean. Okay, and all clean. So what does this do? CD mesh, clean case, and then I believe let's delete everything in tri-surface. Let's delete constant polymesh, and then we go to case. Okay, I forgot to go back here to case, and then clean case. Possibly this should do it. We can try it in case we do have a couple of all clean. Let's go into case. I deleted the 0 folder as well, but that's not very good. Okay, then let's just keep this file, yes, and save it, yes, and save it. Otherwise, I'm going to be... Okay, so that's not what I wanted. Clean case 0, so I think it's clean case. Let's take a look at constant try surface, that's fine. Okay, if I execute case, it still deletes it. Okay, that's not good. Then let's just do this the OpenFOAM way. So yes, yes, and then make a copy of 0.org to 0.org, and then what we will do is now go into case and then cp 0.org to 0. Okay, all clean, and then let's see whether all run works. Snappy Hex Mesh seems to be running. Okay, so are there some questions? Okay, no questions yet. Okay, so Snappy Hex Mesh is running. Let's wait for it to finish. And as I mentioned, if this all run script works, then please test it. Maybe you can find some errors or weaknesses in my case setup. I mean, it is a Wednesday afternoon after a long day, so possibly I made some errors here. So please second guess it and then let me know in the video below what you could improve and what you think could be improved for further simulations, for turbulence simulations. So please make sure to comment on your inputs below the video. Okay, so the simulation seems to be running. So now we have, yeah, so it is running and it's also finished. Yeah, very good. So we have now, yeah, okay, that's good. So we have now an all run script, and we have an all run script. We don't need here the case backup anymore, and we have an all clean script, an all run script, an all run script .pre script, so we can next time improve possibly the mesh and improve the case setup and then compare the drag with the actual curves. So what I will now just quickly do, just run all clean. And then tutorial 3, just create a zip file of this one, and I will upload this to my GitHub account after I end the stream, and I will link it in the description box below. So tomorrow, it takes overnight usually for YouTube to render the live stream, so tomorrow you can rewatch this tutorial, or you can just go to my GitHub account. There is a link on my YouTube channel, and then look for Tut 3, and then you can just play around with the case. Please make sure the next live stream is going to be not next week, because then I'm on vacation, but possibly in 2 weeks, but I will let you know. Okay, so there are no questions. So do you have some questions? So I'm going to wait here a little bit. If there are no questions, that I'm going to just end the stream at this point when we set up the geometry, the first mesh and the first case. We have an all run script, and then next time we can concentrate on the important settings, the layer addition, the resolution, and turbulence modeling, and so on. Okay, so let's just wait if there are some questions. If not, then I will say goodbye. Yeah, so maybe an information I've been working on an overset tutorial. I know I talked about that. I did a recording, but for some reason the quality was not the best. It was medium quality, so it was okay, but I said that I'm going to re-record it because I do want to give you, at least on the normal tutorials which I record and upload to video, I want to give you a certain audio quality and video quality, and I don't want to give you just a standard quality. So the live streams I really cannot change. This is defined by YouTube and the streaming software that I have. So this is what I can give you there, but in the tutorials that I pre-record, I do want to have good quality of the results of the videos. So stay tuned. There is a tutorial with overset mesh upcoming. If you cannot wait, you can go to wiki.openfoam.com/tutorials. It is already up online. Just the guided video tutorial takes a bit longer because I have to re-record it. Okay, I can see Mr. Dippy Daddy. Hi, Mr. Dippy Daddy. How does OpenFOAM deal with new physics? It's C++, so I know it's hard work, but out of 10, what do you mean with new physics? Do you mean string theory, or what kind of new theory? So if you want to add new physics, I guess it's the second one. So so if you want to add your own physics, so it is difficult. So you do have to know a bit of C++ programming. At wiki.openfoam.com/tutorials, if you go to the collection by topic, there are several tutorials on how to program in OpenFOAM. So if you're interested in that, I would advise you to go there, and I can show you. So I'm not sure why I just talk about it. Okay, so if you go to the topics here, there are some programming tutorials that you can check out. Okay, Laviette, can you take up a case of a CAD model and then create patches, that sort of stuff? Case of a CAD model. Yeah, so not CAD directly, so not IGES or step file. You can only use STL and object files, unfortunately. So you have to convert those into STL and then divide the STL into your patches, and then you can run Snappy Hex Mesh. Gas dispersion models from a porous matrix. Difficult to say. So you can add it, but if you want to, you have to program something that, then I would advise you to take a look at these tutorials here. Abdul the doc. Hi Abdul, what is wrong with my notification? Geez, I don't know. Maybe you didn't ring the bell button on YouTube, and then you didn't get the notifications, or YouTube again screwed up with subscribers who rang the bell. So make sure to ring the bell. Theoretically, then you should get the notification immediately. Nick, hi, how can we get force and moment in Z direction in OpenFOAM? So this is something that I now forgot to do. So I also did. So that's something that I'm going to do the next time. So here I put in a question: what is the best way to use the force coefficients? To calculate the force coefficients, and there is a function object for that. Then you can use the force functions and calculate it in ParaView. So you can calculate it in ParaView. I can show you I hope this is what you mean. So you have, okay, no. So I cannot show you. So what I would do is select sphere, only the surface, then take the filter here, integrate variables, and then take a look at the pressure, and of course multiply it with the density, and then this integrated pressure is the overall force. Then there are function objects that can calculate it, but I did not set it up, so that's something for the next tutorial. So if you are interested in that, please make a comment below this video so I don't forget to do this next time. Okay, I'm default late to the foam party. Yeah, so we started at 3 Central European time. Okay, hi Salman, I want to learn turbo machine simulation in OpenFOAM, like centrifugal compression. Do you have any idea about turbo machine simulations? Then please make some tutorials. I'm not an expert. As you know, I'm an editor for the OpenFOAM journal, and I know that there are some submissions, so it is not a simple task, it is a scientific task. So I don't know of any tutorials, so maybe you have to Google it yourself. Abdul's Turbo best solver is CFX by ANSYS. So as I mentioned, I know that people submitted results on turbo machinery in OpenFOAM, so it is also possible, but it's not the easiest task. Okay, one last question by Brandon. Just out of curiosity, have you done any work with adjoint-based solvers? No, this is one of the few solvers and approaches that I've never had the chance to take a look at, because I never worked with the automotive industry in this regard of shape optimization. But I mean, if there is a project where I'm involved in, I would love to, but I don't have any experience in this. Okay, so you're a console guy, Python man. Yeah, so for OpenFOAM you need C++. Samjad, hi, I'm trying to simulate a boat moving in circular path using solid body motion interval. I will be the inlet condition for this, the faraway inlet condition, so that there are specific boundary conditions. So maybe just check out the boundary conditions for that. And maybe the overset tutorial would be something for you, because I also use Interfoam and I'm also moving around something in that tutorial. What is the stability of K omega SST? Mine seems hard to get conversions. Okay, that's interesting, because in my case K omega SST is usually the stablest turbulence model, but maybe it's just an application thing. SimScale, for example. Yeah, sure. Okay, so then we are reaching, so we are now online for over an hour, and we are reaching 4 o'clock, so possibly I will end the live stream at this point. So please make sure to test this tutorial and then make some suggestions in the video that is going to be uploaded on YouTube tomorrow below that, with improvements for next time. Okay, so with that, I would like to thank you for watching and listening, and I hope to see you next time.